Welcome to Microsoft Summit 2020. Good morning, good afternoon, evening. I'm Baolin from Microsoft. I'm going to present our work, Tough Self-Learning End-to-End Dialog. It's a joint work with my manager, Jianwei from Microsoft Research and Professor Meng from the Chinese University of Hong Kong. Here's the agenda. I will briefly introduce the background on TaskBot, followed by our motivation of self-learning and the proposed self-learning TaskBot. Then talk about experiment to validate the proposed framework. Finally, conclude the talk. This is a classical data system architecture. Language understanding component identify user intent. Dialog manager track user goal, make decision on how to respond. Language generation model converts semantic labels on to natural language. With recent advanced neural approach to consider AI, the most common approach of building TaskBot is to train neural model to imitate behavior in a large-scale limited labeled dialog corpora, but it's label intensive. Pre-training and fine-tuning paradigm make large pre-trained model has a limited data scarcity problem to a large extent and become increasingly prevalent for building TaskBot skill. Let's briefly summarize the pros and cons of each method. Conventional simple learning is straightforward, easy to implement, but labor-intensive and prohibitively expensive to collect and analyze large corpus. Pre-training and fine-tuning substantially reduce the required number of annotated training example, but the training data has limited coverage dialog flows. More importantly, this data approach assumes independent identical distribution in data setting. It is the static environment. It tends to fail when confronting other distribution examples. It is a changing environment. Changing environment is pretty common in the context dialog system because of user behavior changes. There's a lot of more variety of language policy in real world than presented in training data. And the second is the data definition changes. The system needs to handle new source value as user and business requirement evolve. Here's an example after deployment. The system failed to provide postal code in the second turn due to user behavior changes. In third turn, the agent successfully respond with the postal code. The interaction are abundant, cheap, and contains potential training signals. We argue that TaskBot should not merely imitate expert behavior in a corpus, but also learn from these human body interactions accumulated after deployment to adapt to changing environment. So in this work, we propose a novel self-learning framework for building TaskBot in a more realistic changing environment setting. It allows bot to adapt to changing environments by learning from the human body interaction after deployment. It consists of two component dialog model. It can be whatever end-to-end model for belief state tracking and response generation. The second is reward model is pre-trained language transform model. It judges the quality of response. It operates in 4 steps. The first is for fine-tuning with limited label data, and then we deploy the model to users and accumulate interaction, and then refine the dialog model with accumulated interactions via reinforcement learning. It budget allowed to recruit human annotator to correct dialogues via machine teaching. The dialog model is self-learning agent is compatible with any end-to-end dialog model. In this project, we employ Soloist as the dialog model, resulting in an agent called self-learning Soloist. We briefly recap Soloist model. It takes dialog history as input and generates belief state, which then used to query database. The results will be part of the input to the model to generate final response. It is pre-trained on public available task-oriented dialog and can be used for quick adaptation to new tasks. The reward model judges the quality in terms of fluency, success, dialog flow consistency. We formulate the task as a binary classification problem. It innate from pre-trained transformer to predict the quality given the context. We integrate auxiliary tasks to enrich the training supervisions. We automatically correct the training example to obtain positive and negative training data. Machine teaching is an effective way to add new knowledge to update the system, especially when we need to handle task definition changes. In our implementation, we use concept linear to visualize the dialog and correct the belief state to add new responses. We conduct experiment on 4 well-studied dialog tasks: attraction, train, hotel, and restaurant. We divide the evaluation setting into 2 parts. Setting 1 to simulate the user behavior changes. The setting 2 task definition changes. We finally present interactive human evaluations. The evaluation metric include inform, success, blue, and the combined score. Inform indicate if the bot tracks correctly entity that match user goal. The success measures if the bot answers all request information. Blue score measures if the responses are fluent and human agent. The combined score is a weighted sum at the overall metrics. We are deploying a training agent to interact with the real human user to collect the interaction are labor intensive, so we create a simulation setting by adding noise into a random dataset to simulate accumulated interaction. 10% of the data will be used for training, 90% crowd data is noisy interaction. Here's the result. We see that self-learning solid perform significantly better than solids, showing that our framework enables learning from unlabeled interaction, but still lag behind the upper bound result, showing there is still a large room for improvement, especially improve the quality of reward model. Simulation setting allows effortless experimental study to validate the effectiveness of proposed method. However, the results are likely biased. Therefore, we conduct human-in-the-loop evaluation. We deploy the trained model to interact with the real user and collect interactions. We collect additional 10% real human-bot interactions. Here's the result. We see that learning from real human-bot dialogues further brings 3-point improvements. We confirm that simulation evaluation and human-in-the-loop evaluation results are consistent, which means that self-learning agent enables bot to learn from interaction to adapt to user behavior changes. For the second setting, task definition changes, we extend the restaurant with additional slot to serve food delivery by adding 4 new slots, resulting in the dominant restaurant extension. 10 examples are obtained via machine teaching for training, 20 real user dialogue for self-learning, and 50 examples for testing. We see that machine teaching is an effective way to teach about task definition changes. Learning from interactions brings 7 points improvement, establishing the effectiveness of self-learning agent to adapt to changing environment caused by task definition changes. We also conduct human evaluation using the same protocol as we used last year when we organized the Dialog challenge. We recruit real human user to chat with our system and rate its performance. We see that the results are consistent as automatic evaluation, demonstrate the capability of self-learning agent for completing tasks in real scenarios. So to conclude this talk, we propose and focus on more realistic changing environment setting for building task bot. We propose self-learning agent, which is a self-learning framework that combines the supervised learning, reinforced learning, and machine teaching for building task bot in a more realistic changing environment setting. Experiment on 4 well-studied experiments show that self-learning agent allow bots to adapt to changing environments by learning from the human-bot interaction after deployment. As to the future work, there are more ways that a task bot could learn to improve itself. For example, human expert could provide not only the correct label but also the feedback in natural language. So we leave learning from natural language from human back as future work. Thanks.